Welcome to the deep dive.
Great to be here.
You know that feeling, right? The world is just accelerating at this unbelievable pace,
It really is.
driven by digital transformation that's reshaping literally every industry. It can feel like a full-time job just trying to keep up.
Yeah, just to understand the core tech driving it all.
Exactly. Well, you're in the right place if you feel that way.
Definitely. Our mission here at the Deep Dive is really to cut through that complexity. We take a stack of the latest research, articles, insights, all that stuff,
Right.
and we pull out the most important nuggets of knowledge for you.
Think of it as your shortcut, yeah, to being truly well-informed without getting bogged down.
Exactly. No information overload here.
And today, we are taking a deep dive into something really fundamental.
The absolute bedrock.
Key IT infrastructure components. Think of us as your guides navigating this landscape of innovation.
Our mission for you today is simple. Give you a clear, structured understanding of these vital components.
We'll explore the building blocks of cloud computing, modern IT. I mean, from what cloud is,
Right. The basics.
to how services get delivered, what makes up the infrastructure itself.
And how it's all managed, secured,
Yeah.
the whole package.
So get ready for some hopefully genuine aha moments. Let's unpack this. Setting the stage. Understanding cloud computing fundamentals. Okay, so let's start with the big one. The elephant in the digital room, you might say. What exactly is cloud computing? We hear it everywhere, but the definition can get a bit hazy.
It definitely can. It's used so broadly. So to bring some universal clarity, we should lean on the U.S. National Institute of Standards and Technology. NIST.
NIST. They're the standard for this stuff, right?
They really are. Their definition has become the de facto standard globally.
Okay, so what do they say?
NIST defines cloud computing as a model for enabling convenient on-demand network access to a shared pool of configurable computing resources.
Okay, wait. Convenient on-demand access, shared pool. What kind of resources?
Things like networks, servers, storage, applications, and services
Got it.
that can be rapidly provisioned and released with minimal management effort or service provider interaction.
Okay, that's quite a definition, packed with ideas.
It really is. But let's unpack those nuggets, like you said.
Yeah. It's about access, right? Getting stuff when you need it.
On-demand access, exactly. And to a shared pool of resources. That's key.
Shared pool, meaning lots of people using the same underlying stuff.
Precisely. It's configurable, you can set it up how you need, and it can be rapidly provisioned. Quick setup.
And released just as quickly, with minimal fuss.
Minimal management effort or service provider interaction, that self-service aspect.
So this definition, it highlights a radical shift from traditional IT, doesn't it?
Absolutely. It's not just about buying servers anymore. It's about access, sharing, speed, and less hands-on management.
That shared pool idea, it seems pretty central.
It is. It implies that multi-tenant model, which is fundamental to how cloud works economically.
How providers make it affordable.
Right. It's how they achieve those incredible economies of scale and really high resource utilization. That drives down costs for everyone.
And the rapidly provisioned and released part.
That points directly to the agility, the self-service nature. That's what really sets cloud apart from waiting weeks for traditional IT.
So it's less about where the computers are and more about how you interact with them.
Exactly. The interaction model is key.
And part of that interaction is understanding who does what. The source mentions a clear distinction, providers and consumers.
Yes, that's crucial. At its core, a cloud infrastructure is built, operated, and managed by a cloud provider. That's the company offering the service.
Like AWS or Google Cloud or Azure.
Exactly. And on the other side, you have the cloud users or consumers, that's you or your organization, using the cloud.
Why is this distinction so important?
Because it clarifies responsibility and control. Who manages what? Where does the provider's job end and yours begin? It's different for different cloud services, as we'll see.
Okay, that makes sense. It shifts responsibility compared to owning everything yourself.
A fundamental shift.
All right, so NIST gives us the definition, but they also break it down further, right, into 5 essential characteristics that really define cloud.
They do. These 5 things really capture the essence of what makes something truly cloud computing.
What's the first one?
The first is on-demand self-service.
Okay, self-service. What does that mean in practice?
Imagine needing, say, more server time or network storage.
Right.
With on-demand self-service, you can provision those resources entirely automatically. You don't need a human interaction with the service provider.
Like clicking a button in a portal.
Pretty much. It's the ultimate easy button for IT resources. It empowers you to get what you need when you need it, immediately.
No more filling out forms and waiting weeks.
Exactly. That speed is critical today.
Okay, characteristic number 1. On-demand self-service. What's next?
Number 2 is broad network access.
Access over the network. That seems obvious for anything online, doesn't it? What makes it essential here?
It means the capabilities are available over the network and accessed through standard mechanisms.
Standard mechanisms, like web browsers.
Web browsers, standard protocols like SOP and REST for web services. This promotes use by a really diverse range of devices.
Ah, so not just your desktop.
Nope. Mobile phones, tablets, laptops, workstations, pretty much anything with a network connection.
So you can get to your cloud services from basically anywhere, on almost anything.
That's the goal. Universal accessibility.
Makes sense. Okay, number 3. This sounds like a big one. Resource pooling.
It's absolutely foundational. Resource pooling means the provider's computing resources are, well, pooled together.
With a big shared pot.
Exactly. A shared pool to serve multiple consumers using what's called a multi-tenant model. Resources are dynamically assigned and reassigned according to demand.
Multi-tenant. Like an apartment building where everyone shares the foundation and utilities.
That's a great analogy. Multiple independent consumers drawing from the same resource pool.
And virtualization plays a big role here.
Oh, huge. Virtualization is a key enabler. It allows providers to abstract the physical hardware and achieve those massive economies of scale we talked about.
Right. And super high resource utilization. No wasted hardware.
Which, again, drives down costs for you.
Okay, pooling resources. Number 4 sounds exciting. Rapid elasticity.
This is one of the cloud's superpowers, really. Agility personified, as you said.
Elasticity.
Yeah.
Like stretching and shrinking.
Precisely. It's the ability for you, the consumer, to quickly request, receive, and then release as many resources as you need.
Up to some limit, I guess.
Up to a defined limit, yes.
Yeah.
But the key is the speed and flexibility. Capacity can be elastically provisioned and released.
Scaling out to add more resources?
And scaling in to release them when you don't need them anymore.
So it matches demand perfectly.
Exactly. This is absolutely crucial for handling unpredictable workloads. Think about an e-commerce site during a huge sale.
Right. They need massive capacity for a short time, then it drops off.
Rapid elasticity handles that perfectly. You get the capacity you need, then release it. No over-provisioning, no running out.
That's a game changer for efficiency and cost. Which leads nicely to the last characteristic, right? How do you pay for all this dynamic stuff?
Number 5, measured service.
Measured service, like a utility meter.
Exactly like that. Your cloud electricity bill, essentially. Cloud systems automatically control and optimize resource use by leveraging a metering capability.
Metering what exactly?
It can be at various levels of abstraction, storage usage, processing, bandwidth, active user accounts.
Right.
Depends on the service.
Okay.
This metering provides transparency for both the provider and you, the consumer.
So you know what you're using.
And it enables those pay-per-use or pay-as-you-go billing models. You only pay for what you actually consume.
Just like your electricity bill.
Precisely. And this is more than just billing transparency. It fundamentally shifts IT spending. It moves IT from a capital expensive, buying big, expensive servers that might sit idle half the time.
Right, CapEx.
To a true operational expense, OpEx. You pay for what you use. This eliminates waste and gives businesses huge budget flexibility.
Freeing up money for other things.
Like innovation.
Yeah.
Instead of just keeping the lights on.
Okay, those 5 characteristics, on-demand self-service, broad network access, resource pooling, rapid elasticity, and measured service, really paint a clear picture.
They define what makes cloud, cloud.
So connecting this to the bigger picture, what are the main benefits for businesses actually embracing cloud computing? Why make the switch?
Well, there are several really compelling benefits driving this massive adoption. First, a huge boost in business agility.
Speed, right.
Speed. Cloud lets you provision IT resources incredibly quickly. We're talking minutes or hours, not weeks or months.
So you can deploy new applications, new services much faster?
Dramatically faster. This means faster time to market for new ideas and quicker responses to market changes. That's a massive competitive edge.
Huge. And then the one everyone talks about, reduced IT costs.
Always a major driver. By renting resources on a pay-per-use or subscription basis, you significantly cut capital expenditure. CapEx.
No more buying those big, underutilized servers.
Exactly. You eliminate that waste. Plus, you cut expenses related to managing the infrastructure, the physical space, power, cooling. It all adds up.
And that freed up budget.
Could be reinvested into innovation, driving the business forward.
Makes sense. What about reliability? Does cloud help there? The source mentions high availability.
Yes, cloud computing is typically designed for high availability, often far beyond what a single organization could affordably build themselves.
How do they achieve that?
Through redundancy. Redundant infrastructure components, compute, network, storage, and clustered software. It builds in fault tolerance.
Services are more resilient to failures?
Much more resilient generally, more reliable.
Okay. And for the poor IT teams managing everything, it sounds like a relief. Simplified IT management.
Oh, absolutely. Many traditional IT maintenance tasks, software updates, hardware refreshes, patching, are handled by the cloud provider.
Taking that burden off the internal team.
Completely. It frees up your IT staff to focus on strategic initiatives, things that add direct value to the business, rather than just routine operational stuff.
Shifting from maintenance to innovation.
That's the goal.
And finally, something that feels almost essential now, flexibility of access.
Indeed. In the cloud model, your applications and data live centrally in the cloud.
Not tied to a specific machine.
Exactly. So they're accessible from anywhere on pretty much any device, desktop, mobile, tablet, thin client.
Which enables things like BYOD, bring your own device.
It's a key enabler for BYOD, yeah. It frees users from being tied to a specific work computer. You can access your work from anywhere.
It's really about working smarter.
Smarter, more flexibly. 2, the delivery spectrum. Cloud service and deployment models.
Okay, we've got the fundamentals down. We know what cloud is. Now let's talk about how these cloud services are actually delivered.
Right. This brings us to the different ways cloud is packaged and deployed. We need to look at the cloud service models and the deployment models.
2 key concepts to understand the options.
Absolutely. And understanding these helps you choose the right cloud strategy for different needs. NIST, again, in their special publication 800-145, outlines the main service models.
Okay, let's start there. Service models. The most fundamental one, the base layer, is infrastructure as a service, right? IS.
That's it. IS provides you with the core raw computing resources.
Like what specifically?
Processing power, virtual CPUs, storage, virtual disks, networks, virtual networks, other fundamental resources. Basically, virtual servers, storage, network connections.
So the provider gives you the building blocks.
You then deploy and run your own arbitrary software on top. That includes operating systems in your application.
So who controls what in IS?
The provider manages the underlying cloud infrastructure, the physical hardware, the virtualization layer. You, the consumer, have control over the operating systems, storage, deployed applications.
Pretty much everything from the OS up.
Right. And maybe limited control of some networking components like firewalls.
Can you give some real-world examples?
Sure. Think Amazon EC2 Elastic Compute Cloud for virtual servers, or Amazon S3 Simple Storage Service for storage.
Okay. So IaaS is like renting the raw land and utilities. You build the house yourself.
That's a good way to put it, renting the building blocks for your digital infrastructure.
Got it. Moving up the stack then, we hit platform as a service, PaaS. What's the shift here?
With PaaS, the capability provided to you is to deploy your applications onto the cloud infrastructure.
So you're not managing the OS anymore?
Nope. You don't manage or control the underlying cloud infrastructure network, servers, OS, storage. That's all handled by the provider.
What do you manage then?
You focus purely on deploying your applications and maybe some configuration settings for the application hosting environment itself.
Using tools the provider gives you.
Exactly. Programming languages, libraries, services, tools supported by the provider.
So if IaaS is renting the land, PaaS is like renting a workshop.
Yeah.
With all the tools ready.
Yeah, or maybe like having the foundation and frame of the house built. You focus on the interior design and functionality or code.
What are some examples of PaaS?
AWS Elastic Beanstalk, Microsoft Azure App Service, Google App Engine. These are classic PaaS examples.
Perfect for developers who just want to code, right? Without worrying about servers.
Exactly. It speeds up development significantly.
Okay, IaaS, PaaS. The highest level of abstraction is software as a service, SaaS.
That's right. SaaS is the model most people interact with daily, often without even realizing it's cloud.
How does it work?
With SaaS, you, the consumer, simply use the provider's applications. These applications are running on a cloud infrastructure.
And you access them how?
Typically through a thin client interface, like a web browser,
Well,
or maybe a mobile app.
so what do you control in SaaS?
Virtually nothing about the underlying infrastructure. Network, servers, OS, storage, all invisible. Even application capabilities are mostly fixed.
Your control is limited to.
User-specific configuration settings, like your profile, maybe some layout options. The provider manages everything else.
It's like renting a fully furnished apartment then. You just move in and use it.
Perfect analogy. You just use the software.
Examples must be everywhere.
Oh, yeah. Salesforce.com for CRM, Google Workspace, Gmail, Docs, Microsoft Office 365. These are all everyday SaaS examples.
So those are the three core NIST models, IaaS, PaaS, SaaS. But the source also mentions XaaS, anything as a service.
Yeah, XaaS, or sometimes EAS for everything as a service, has emerged beyond those core models.
What does it represent?
It's really an umbrella term. It describes this growing smorgasbord of specialized, utility-based offerings accessible on demand over the internet.
So more niche services?
Could be database as a service, security as a service, monitoring as a service. Pretty much anything that can be packaged and delivered via the cloud.
Bruh.
It signals a future where almost any IT capability can be consumed as a service.
Fascinating. The cloud just keeps expanding its reach.
It does.
Okay, that covers the service models, what you get. Now let's look at the deployment models, where and how the cloud is set up.
Right. The deployment model determines how the infrastructure is built, who owns it, and who can access it.
Starting with the most, well, public one, public cloud.
The public cloud infrastructure is provisioned for open use by the general public. Anyone can sign up and use it.
Who builds and runs it?
It's built, owned, and operated by a cloud provider. Think business, academic, or government organizations, or a combination. But the key is, it exists on the premises of the cloud provider, like Google, Amazon, Microsoft.
What's the big advantage here?
Low upfront expenditure is huge. You don't buy any hardware, and you get access to enormous scalability, immense resources without owning them.
Sounds great. Are there downsides or considerations?
Well, concerns sometimes arise around network availability or relying on the internet and the provider's networks. Also, the risks associated with multi-tenancy sharing infrastructure with others, and sometimes limited visibility or control over your resources and data compared to owning it.
Trade-offs, as always. But why do businesses choose it?
Our sources, referencing IDC reports, highlight agility, cost reduction, and innovation as the top drivers. A startup, for example, can instantly get global reach without building data centers. That's incredibly powerful.
Okay, public cloud. Now the opposite end. Private cloud.
A private cloud infrastructure is provisioned for the exclusive use of a single organization comprising multiple consumers, like different business units.
So not shared with the public.
Exactly. Services are dedicated to internal consumers only.
What's the main benefit there? Control.
Control and privacy, absolutely. It offers a greater degree of control over the infrastructure, applications, and data, and enhanced privacy and security.
Crucial for some industries, right?
Definitely. Organizations with strict regulatory requirements like finance or healthcare, or those with highly sensitive intellectual property, often prefer private clouds.
Can a private cloud be located anywhere?
It can vary. It might be owned, managed, and operated by the organization itself or a third party or some combination, and it can exist on-premise.
In their own data center.
Right. Or it could be externally hosted, outsourced to a provider, but kept logically and often physically separate from public cloud resources.
What drives businesses to choose private cloud?
Often drivers include reducing the total cost of ownership compared to traditional IT, achieving high performance for specific workloads, meeting stringent security needs, and maintaining strong IT control.
Okay, public, private. What about something in between? Community cloud.
Community cloud is an interesting one. The cloud infrastructure is provisioned for exclusive use by a specific community of consumers from organizations that have shared concerns.
Shared concerns like what?
Maybe a specific mission, security requirements, policy or compliance considerations. Think of maybe a group of universities or government agencies within a specific area, or companies in a regulated industry.
So they share the infrastructure.
Yes, it may be owned, managed, and operated by one or more of the organizations in the community, a third party, or a mix. Costs are typically shared among the community members.
What are the benefits there?
It offers a balance. You get higher control and privacy than a public cloud, but you share the costs among a smaller, trusted group, making it potentially more affordable than a fully private cloud.
Like a private club, almost?
Sort of. And like private cloud, it can be on-premise or externally hosted.
Right. Now, the model that seems to get the most attention for flexibility, hybrid cloud.
Hybrid cloud is where things get really interesting, strategically. It's a competition of two or more distinct cloud infrastructures.
Mixing and matching.
Exactly. Private, community, or public clouds, they remain unique entities, but they're bound together
Bound together how?
by standardized or proprietary technology like APIs that enables data and application portability between them. Think of moving workloads back and forth.
So you get the best of both worlds.
That's the idea. It allows organizations to leverage the best features of different cloud types for different jobs.
What are some key use cases? The source mentioned cloud bursting. That sounds dynamic.
Cloud bursting is a classic hybrid use case. It allows you to run your normal, everyday workloads in your private cloud.
Where you have more control.
Right. But then you can temporarily access public cloud resources to meet transient, higher workload demands.
Like that e-commerce example during a sale.
Perfect example. Host your mission-critical stuff like the checkout process on your private cloud, but maybe burst the less critical, more dynamic web pages or product images to the public cloud to handle those sudden traffic spikes.
What's the benefit?
You ensure service availability without having to build out massive, expensive capacity in your private cloud that sits idle most of the year. It saves costs and handles peaks.
Very clever. Any other big use cases?
Application development and testing is another common one. Many organizations use the public cloud for its agility and scalability during the dev and test phases.
Where speed matters.
Exactly. And then they deploy the stable, tested applications to their private cloud for production, maybe for security or compliance reasons.
The source mentioned ADT security using hybrid cloud.
Yes, a real-world example showing how a company benefited from adopting hybrid solutions for their security services, balancing control and flexibility.
Makes sense. Now, one more term that sounds similar but is different, multi-cloud. How does that compare to hybrid?
Good question. The terms are often confused. Multi-cloud strategy means adopting and using services from multiple cloud providers.
Like using AWS for one thing, Azure for another, Google Cloud for something else.
Precisely. Unlike hybrid cloud, these different cloud environments aren't necessarily directly interconnected for bursting or workload mobility.
So why use multiple clouds then?
It's about choosing the best tool or the best price for each specific job or workload. No single cloud provider or model suits all requirements.
So you might run analytics on Google Cloud because it's good at that, but your main website on AWS.
Exactly. Some applications just perform better or are more cost-effective on one platform versus another. It also helps organizations avoid vendor lock-in. You're not tied to a single provider.
That seems like a growing trend.
Definitely. That 2017 RightScale report mentioned in the source showed the vast majority of enterprises were planning to use multiple cloud infrastructure services. It's become the norm, really. 3. The cloud reference architecture, building blocks for success.
Okay, we've covered the types of cloud, the service models, the deployment models. Now let's get into the actual structure. How is a cloud environment built?
Right. This brings us to the cloud reference architecture. Think of it as the blueprint.
A blueprint for building clouds.
Exactly. It's an abstract model that characterizes and standardizes the functions of a cloud computing environment. It lays out the core components and how they fit together.
What are those core components?
It generally includes the applications running on top, the modern infrastructure layer, which itself has physical, virtual, and software-defined parts.
Okay.
An orchestrator to manage everything, and the service elements that are delivered.
Does it define functions too?
Yes, it also defines 3 core functions that span across the architecture: business continuity, security, and service management. We'll dive into those later.
And it connects to other clouds.
Crucially, yes, it includes cloud extensibility, allowing it to connect to external clouds, enabling those hybrid cloud models we just discussed.
Got it. A comprehensive blueprint. Let's start at the top then, the application layer. Applications are what users see, right? The face of digital transformation.
Absolutely. Software apps are constantly evolving and impacting business. We can broadly classify them as traditional and modern.
Okay, let's look back first. Traditional applications and their challenges. What were they like?
Traditional apps were often monolithic.
Monolithic.
Built as a single, large, tightly coupled, executable file or unit. Think one giant piece of code doing everything.
What problems did that cause?
It led to really long development and update cycles. Changing one small part could risk breaking the whole thing. They were difficult to maintain and lacked agility.
Designed for older ways of working.
Often designed desktop first, scaled vertically, meaning you just bought a bigger server to handle more load, and they really relied on the underlying infrastructure being perfectly reliable.
So they impeded agility.
Hugely. IT often provided a fixed stack of tech, planned way in advance. Developers spent more time configuring infrastructure than actually coding new features.
Not ideal for today's demands.
Not at all. Modern customer expectations, dynamic interactions, mobility, personalization demand a shift. Every company is becoming a software and data-driven company now.
Which leads us to modern cloud-native applications. The path forward. How are these built differently?
These applications are designed from the ground up to take full advantage of modern IT infrastructure, especially the cloud.
So, not monolithic.
Definitely not. They're typically modular, component-based, designed to perform in a distributed fashion across multiple machines or services.
And they handle failure differently.
Critically, yes. They expect failure. Resilience is built in. They support predictive or reactive scaling, that elasticity we talked about, and have a minimal footprint.
The goal is speed.
Speed and agility, delivering new features or services in hours or days, not weeks or months.
The source mentioned the 12-factor app. Is that like a rule book for building these?
It's a set of best practices, really. Developed by Heroku, an early cloud pioneer back in 2012. It guides developers in building robust, reliable, modern apps that are perfect for cloud deployment and scaling.
Can you give an example of a factor?
Sure. One is DevPod parity, keeping your development, staging, and production environments as similar as possible.
Why is that important?
It dramatically reduces bugs caused by environment differences and allows for much shorter cycles, hours, not days or weeks, between writing code and getting it live.
Another example.
Another is treating logs as event streams, not just static files, but continuous streams of data that orchestration tools can easily parse, create alerts from, and use for debugging. It makes managing distributed systems much easier.
So it's about building apps designed for the cloud environment. And a key architectural style for this is microservices architecture.
Yes. Microservices are a way to decompose those old monoliths.
How does it work?
The application is broken down into small, loosely coupled, independently operating services. Each service focuses on a specific business capability.
Running independently.
Each runs in its own process and typically communicates with others using lightweight mechanisms, often REST APIs.
What's the big advantage of breaking things up like that?
Several huge ones. First, it speeds up deployments dramatically. Each microservice can be deployed, upgraded, scaled, and even restarted independently of the others.
So a change to one service doesn't require redeploying the whole application.
Exactly. This enables continuous integration and continuous delivery, CI/CD. Teams can work on different services concurrently and release updates much faster.
What about failures?
It improves fault isolation. If one service has a problem, like a memory leak, it doesn't necessarily crash the entire application. The impact is contained.
And technology choices.
It eliminates long-term commitment to a single technology stack. Different services can be written in different languages or use different databases, whatever makes sense for that specific service.
The source mentioned a real-world anecdote.
Yeah, it talked about a large entertainment company, likely Netflix, transitioning from a monolithic DVD rental app to hundreds of microservices for streaming.
What did that enable them to do?
It allowed them to scale to millions of users globally, achieve incredible uptime, like 247 availability, optimize for speed, and dramatically accelerate development. Different teams could work independently on different services. It was a massive transformation.
Wow. And how do you package these microservices for deployment? That brings us to containers, right?
Containers are the perfect packaging mechanism for microservices.
What are they exactly? Lightweight VMs?
Sort of, but lighter. They're standalone, executable packages that contain everything needed to run a piece of software. The code, runtime, system tools, libraries, config files.
But they don't include a whole OS like a VM does.
Correct. They share the OS kernel of the host system.
Yeah.
That's what makes them so lightweight and resource efficient compared to VMs.
And Docker played a big role here.
Docker, the open source project, massively boosted container adoption. It provided tools and standards that made containers much easier to build, ship, and run, ensuring portability without code changes.
Portability, meaning they can run anywhere.
Pretty much anywhere, a developer's laptop, on-premise servers, any public cloud. This enables seamless workload migration and flexible scaling, both horizontally, adding more containers, and vertically resizing them.
Ideal for microservices, then.
Absolutely. Each microservice can be packaged in its own container and instantiated quickly whenever needed. Very efficient.
Okay, so we have modern apps built as microservices packaged in containers. How are these actually delivered and managed as services in the cloud?
That brings us to cloud service and orchestration.
What is a cloud service fundamentally?
At its heart, it's just a pack of IT resources, compute, storage, network, maybe specific software made available by a cloud service provider.
And when you actually order and set one up?
Once it's provisioned and configured for you, it becomes a service instance. Think of that IaaS example. 3 VMs, app, DB, test, with specific network settings and storage attached. That whole configured unit is a service instance.
How do users find and order these services? Through the cloud service catalog and portal.
Exactly. The service catalog is the menu. It's where providers define, publish, and manage their offerings.
What information is in the catalog?
Things like the service category, name, description, features, options, price, maybe the estimated provisioning time. Dell EMC even has one for private cloud services, the source notes.
And this catalog enables self-service.
Precisely, is how you browse and select what you need.
And the cloud portal is the interface for that.
Right. The cloud portal is typically a web portal that presents the service catalog and other cloud interfaces. It lets consumers order and manage their services.
Administrators use it too.
Yes, administrators use it to manage the underlying infrastructure as well. It often personalizes the content based on who you are and what your role is.
So it's the front door to the cloud services.
It is. It presents information and interacts with the orchestration layer behind the scenes, sending requests and getting responses.
Okay. Once a service is ordered, it goes through a life cycle, right? The cloud service life cycle.
Yes, there are 4 key phases, generally aligned with business strategy from start to finish.
What's the first phase?
Service planning. This is where cloud administrators figure out what services to offer, assess IT readiness, define service roadmaps, and handle the financial side, budgeting, accounting, chargeback models.
Charging departments for usage.
Right, or showback, which just reports the cost without actually charging, planning how costs will be handled.
Phase 2.
Service creation. This is where the technical details get defined. Service templates. The collections of hardware-software components are created. These are then combined into service offerings with specific constraints, policies, pricing, and service level agreements, SLAs.
Building the items for the catalog.
Essentially, yes.
Yeah.
Defining what will be offered.
Then comes the longest phase, service operation.
This is the ongoing phase where the cloud infrastructure and all the deployed services are maintained day to day.
What does that involve?
A lot. Monitoring, configuration management, change management, capacity management, performance tuning, handling incidents and problems, availability management, security management.
Wow. The goal here must be automation.
Significant automation is key to managing all this effectively and efficiently.
And the final phase.
Service termination. The end of the line for a specific service instance or the relationship with the consumer.
What happens then?
It involves deprovisioning the service instances, handling the consumer's data according to the contract, like returning or deleting it, providing a final bill, and maybe gathering feedback. Reasons for termination can vary. Maybe the need was temporary, or the consumer's moving elsewhere.
Okay, that life cycle makes sense. You mentioned automation being key in service operation. Let's talk about the power of service automation. What's the problem it solves?
The challenge with traditional IT is often silos. Different teams manage compute, storage, network, and getting anything done requires manual handoffs, approvals, paperwork.
Which slows things down. A lot.
Hugely. It creates delays and inefficiency, severely impacting time to market for new business services.
So the need is?
Speed. Speed is critical today. IT has to transform to make services easier and faster to consume and manage. Automation is the way to overcome those traditional provisioning and management bottlenecks.
How does it work in practice?
Users request services via those self-service portals we talked about.
Right, the catalog.
Then, orchestration and automation software takes over. It interacts directly with the cloud infrastructure components, hypervisors, storage arrays, network switches to provision resources, and trigger tasks automatically, based on predefined workflows.
Taking the manual steps out.
Eliminating predictable, repeatable manual steps is the core idea. That achieves business agility.
This sounds like the job of service orchestration, the automated conductor.
That's a perfect description. Orchestration software, or an orchestrator, is the brain of the automation.
What does it do?
It programmatically integrates and sequences various system functions into automated workflows to provide and manage cloud services. It coordinates complex tasks across different systems.
How does it talk to all those different systems?
Through application programming interfaces APIs. The orchestrator uses APIs to talk to hypervisors, storage systems, network controllers, monitoring tools, ticketing systems, everything.
So it can bind together multiple functions.
Exactly. Deploying a new application might involve talking to the compute virtualization platform to spin up VMs, the storage system to create volumes, the network system to configure VLANs, the monitoring system to add checks. The orchestrator coordinates all of that.
Based on defined workflows.
Yes. Orchestrators use workflow models built from elements like tasks, automated or manual, approvals, notifications, conditional logic, wait times, even calling other child workflows.
Any examples of orchestration tools?
VMware Visualize Orchestrator and Visualize Automation are mentioned in the source. They accelerate provisioning and delivery across infrastructure, containers, apps, leveraging extensible frameworks for full lifecycle management. There's even a customer story about Vistra Energy transforming their IT using Visualize Automation for stability, reliability, and agility.
So orchestration is really the key to unlocking the speed and efficiency of the cloud model.
Absolutely fundamental. 4. The core, modern infrastructure options.
All right, we've looked at apps, services, orchestration. Let's dig down to the very core now. The actual modern infrastructure options that everything runs on. We have to start with the physical stuff, right?
We've got to start with the tangible foundation. Physical infrastructure.
What are the main building blocks here?
At the very bottom, you have 3 main categories. Compute systems, the cause are ground, the servers doing the processing, storage devices and systems holding the data, and network systems connecting everything.
Okay, let's break down compute systems. What's inside a typical server?
The core components are processors, CPUs, often with multiple cores these days. Random access memory, RAM, for active data. Read-only memory, ROM, for firmware. The motherboard connecting it all. And input-output devices like network interface controllers, NICs, for network connection, and host bus adapters, HBAs, for storage connection.
And servers come in different shapes and sizes.
They do. You've got traditional tower compute systems like standalone desktop PCs, but bigger. They're scalable by just adding more towers, easier to cool, but bulky and cabling gets messy.
Then there are rack-mounted compute systems.
Right, these slide horizontally into standard racks. Saves floor space, simplifies cabling, but each server needs its own power, cooling support within the rack.
And the densest option, blade compute systems.
Blades are really just electronic circuit boards with the core processing components, CPUs, memory, maybe integrated network storage controllers. They slot into a chassis.
What's the advantage of blades?
High density. You fit a lot of compute power in a small space. They share power, cooling, networking, and management through the chassis, which significantly reduces cabling and simplifies management.
Okay, that's compute. Now, storage devices. What are the main types?
The classic is magnetic disk drives, HDDs, spinning platters with read-write heads. Cost-effective, high capacity, but they have mechanical latency.
Slower. Then the faster option, solid-state drives, SSDs.
SSDs use semiconductor-based memory, like flash drives, no moving parts. This means ultra-high performance measured in IOPS, input-output operations per second, very low response times, and they use less power.
But they cost more.
Highest cost per gigabyte, typically yes. But prices are always coming down. They also generally have a longer lifetime than HDDs.
Any others? Optical?
Optical disk drives using lasers for CDs, DVDs, Blu-ray. Less common for primary storage now, more for archiving or distribution.
So those are the drives. How are they organized into storage systems?
There are 3 main types of storage systems based on how data is accessed. First, file storage, often called network-attached storage, or NAS.
NAS, like a shared drive on the network.
Exactly. It enables clients to share files over a standard IP network using protocols like NFS or CIFS. It consolidates data into a central pool. In the cloud, this is often offered as cloud file storage, CFS.
Okay. Second type, block storage.
Block storage provides compute systems with block-level access to storage volumes, typically over a dedicated network like a SAN, storage area network. The file system is created on the compute system itself. Think of it like presenting a raw disk drive to the server. Cloud block storage, CBS, is the cloud service version.
Or disk access. And the third type, becoming very important for cloud, object storage.
Object storage stores file data as objects. An object includes the user data itself, plus metadata information about the data, and maybe user-defined attributes.
How are objects identified?
Each object gets a unique ID, often a hacked value. You access the object using this ID without needing to know its physical location. It uses a flat address space, not hierarchical folders.
What's the benefit of that?
Massive scalability. It's ideal for storing huge amounts of unstructured data, like photos, videos, backups, archives. It's often accessed via web service protocols like REST and SOAP-Parrots. The source mentions OpenStack Swift as an example for object storage uploads.
Okay, compute storage. The final physical piece is network systems.
The glue that holds it all together. We can think of 2 main types of networks here.
First,
Compute-to-compute networks. This is typically your standard IP network, connecting servers to each other and to users. Uses NICs, physical switches, routers. Having enough bandwidth and ports here is crucial for performance.
And the second type connects compute to.
Compute-to-storage networks. This connects servers directly to storage systems, often over a dedicated storage area network, or a SAN.
What's a SAN?
A SAN is a high-speed network specifically for block-level storage traffic. It allows multiple servers to share storage resources and centralizes management. Common types include Fiber Channel SAN, FC-SAN, IP SAN, using protocols like ISCSI, and Fiber Channel over Ethernet SAN, FSUKI SAN.
Okay, that covers the physical layer. Now, the magic happens when we abstract this with virtual infrastructure.
This is where things get really powerful for cloud. Virtualization is the process of abstracting those physical resources, compute, storage, network, to create logical, pooled resources.
What are the big benefits?
Consolidation is a huge one. Running many virtual machines on fewer physical servers optimizes utilization, cuts hardware costs, saves space, uses less power.
It simplifies things, too.
Simplifies infrastructure management, definitely, and increases flexibility through the dynamic creation and reclaiming of virtual resources. It's a key enabler for cloud characteristics like resource pooling and rapid elasticity we discussed earlier.
Let's start with compute virtualization. This is VMs, right?
Yes. Compute virtualization decouples the physical hardware from the operating system and applications. It lets multiple isolated operating systems run concurrently on a single physical system.
And those isolated OS instances are virtual machines, VMs.
Correct.
Yeah.
Each VM is a logical compute system with its own virtual hardware, virtual CPU, memory, storage, network adapters on which you run a guest OS and your applications. Each VM is completely isolated from others on the same physical host.
What's the software that does this? The hypervisor.
The hypervisor is the virtualization software installed on the physical compute system. It's what creates and manages the VMs.
Are there different types of hypervisors?
Yes, two main types. Type 1, or bare metal hypervisor, is installed directly onto the system hardware without an underlying host OS. Think VMware, ESXi, or Microsoft Hyper-V. These are designed for enterprise data centers and have direct hardware access.
And Type 2.
Type 2, or hosted hypervisor, is installed like an application on top of an existing operating system, like Windows or Mac OS. Examples include VMware Fusion or VirtualBox. All hardware requests from the VMs have to go through the host OS.
Is there a security difference?
Yes. The source mentions an interesting security insight. The bare metal hypervisor generally has a smaller, trusted computing base, TCB, fewer critical components that need to be secure. This potentially means fewer security vulnerabilities compared to a hosted hypervisor, where the underlying host OS itself could be an attack vector.
Interesting point. The source had a real-world impact story for compute virtualization.
It did. An educational institution struggling with performance bottlenecks for engineering apps on leased PCs, they switched to virtualized desktops using compute virtualization.
What was the result?
It solved the delays, dramatically improved application responsiveness for the students, and freed up IT staff time previously spent managing all those physical PCs. Showed the real benefits of VM efficiency and isolation.
Okay, compute virtualization. What about storage virtualization?
Storage virtualization abstracts the physical storage devices, pooling storage capacity from potentially heterogeneous systems into a shared pool.
And then you carve out storage from that pool.
Exactly. You create virtual volumes, like LUNs, logical unit numbers, from this aggregated pool and present them to servers.
The source mentioned thin LUNs as an innovation here.
Yes, thin provisioning is fascinating. With a thin LUN, physical storage doesn't need to be allocated when the LUN is created. Storage is allocated dynamically on demand, only when data is actually written to the LUN.
So you don't waste space.
Precisely. It dramatically reduces capital expenditure on storage because you don't have to buy all the capacity up front based on estimates. It improves utilization significantly by preventing over-provisioning. You only pay for or consume physical space as you truly need it.
Very efficient. Now, network virtualization. This creates virtual networks on top of physical ones.
That's the core idea. Virtual LANs, VLANs, are a common example. A VLAN is a logical network created on a physical LAN switch. It lets you group devices together logically, regardless of their physical location, maybe based on department or function.
For better organization and security.
Yes. Private VLANs, PLANs, take it further, allowing more granular isolation within a single VLAN. Then there are more advanced concepts like VXLAN, Virtual Extensible LAN.
What does VXLAN do?
VXLAN creates a Layer 2 overlay network on top of an existing Layer 3 infrastructure. It uses encapsulation to make it much easier to scale out cloud networks while logically isolating potentially thousands of different consumers or tenants. It also helps with VM mobility over longer distances.
And stretched VLANs.
A stretched VLAN extends a single VLAN across multiple physical sites, typically over a wide area network RAN. This allows VMs to move between sites without needing network reconfiguration, which is great for high availability clusters or disaster recovery.
Similar concept for SANs, virtual SANs, vSANs.
Yes, a vSAN is a logical fabric created on a physical fiber channel, or FCES-SAN. It allows you to group nodes together logically, again, independent of physical location, often for security or management purposes.
So all these virtualization layers, compute, storage, network enable, resource pooling. Right?
Yep, they are the key enablers. Resource pooling is that logical abstraction of all the aggregated computing resources, processing power, memory, storage capacity, network bandwidth, managed collectively as shared pools.
And cloud services grab resources from these pools.
Dynamically, yes. When the service needs resources, it gets them from the appropriate pool. When the service releases the resources, they go back into the pool for reallocation to someone else.
How are these pools managed?
They're designed and sized based on anticipated service requirements. A cloud administrator can dynamically create, remove, expand, or shrink pools as needed using management software.
Can you give an example?
Imagine a processor pool that aggregates the CPU power from dozens of physical servers into one logical pool. Or a storage pool combining the capacity of multiple storage arrays into a single vast resource from which LUNs or volumes are provisioned on demand. It maximizes efficiency and flexibility across the entire data center.
That pooling concept is really central to the cloud model.
Absolutely fundamental.
Now, let's move to the intelligent layer that automates and controls all this. Software-defined infrastructure, SDI. What was the problem SDI is trying to solve?
The big challenge with traditional IT was those rigid infrastructure silos. Each application often had its own dedicated stack. Compute, network, storage, security, management.
All separate and vertically integrated.
Right. This created immense complexity, drove up costs, limited resource sharing between silos, and made provisioning new services incredibly slow and cumbersome.
So what's the SDI vision?
SDI is an approach to abstract, pool, and automate all the resources in a data center environment, compute, storage, network, security, to deliver IT as a service.
Controlled by software.
Exactly. Intelligent, policy-driven software controls and manages everything, breaking down those hardware silos and moving beyond hardware-centric architectures.
The source mentioned 4 planes in SDI architecture.
Yes. It helps to think about the different functional layers. The data plane is where the actual data traffic flows, packets moving from port to port.
Okay, the workhorse layer.
Then, crucially, the control plane is decoupled from the data plane. It's typically external software, a controller that provides the programming logic and policies for how the data plane should process and forward traffic. It's centralized and can apply policies consistently across potentially multi-vendor hardware. It also provides APIs for management tools.
So the intelligence is separated from the hardware doing the forwarding.
That's the key idea. Then you have the management plane, which consists of the tools and orchestrators used for overall infrastructure management.
And finally, the user-facing part.
The service plane. This presents the IT resources as services through that self-service portal and service catalog we talked about, allowing users to request and provision what they need.
So what are the key attributes that define SDI?
Several key things. Abstraction and pooling, creating those multi-tenant resource pools from potentially heterogeneous infrastructure.
Right. Shared resources.
Automated, policy-driven provisioning. Services, including related things like data protection, are dynamically created and configured based on predefined policies, not manual steps.
Makes it faster and consistent.
Unified management. A single point of control, ideally for the entire infrastructure, physical and virtual, across multiple vendors. Reduces complexity.
What else?
Self-service via the catalog. Metering to measure resource usage for chargeback or optimization. And it needs to be open and extensible, allowing integration of multi-vendor hardware and external management tools through open APIs.
Okay. What are the core components that make up an SDI environment?
You can think of it in 3 main pillars mirroring the physical infrastructure. First, software-defined compute, SDC.
Which is basically compute virtualization.
Essentially, yes. The hypervisor decouples the OSAPs from the physical hardware and encapsulates them in VMs. The key SDI aspect is that the VM hardware configurations and management are defined and maintained entirely by software, moving away from hardware-centric thinking.
Makes sense. Second pillar, software-defined storage, SDS.
With SDS, an SDS controller software manages storage-related operations independently of the underlying physical storage hardware.
It abstracts the hardware.
Yes, it abstracts the physical details like drive types, RAID levels, locations, and presents virtual storage resources like block volumes or file shares to consumers. Its functions include discovering storage resources, abstracting and pooling them, and provisioning services via the catalog based on policies like performance or capacity tiers. Dell EMC VIPR SRM is mentioned as an example tool for visualizing and optimizing storage in an SDS way.
And the source mentioned Colt Technology Services using Dell EMC VIPR.
Right, showcasing the real-world benefits of adopting SDS for data center modernization.
And the third pillar, software-defined networking, SDN.
SDN brings that software control to the network. An SDN software controller manages network switching and routing functions.
Separating control and data planes again?
Exactly. It abstracts the physical network components, switches, routers, and separates the control plane functions, figuring out where traffic should go, from the data plane functions, actually forwarding the traffic. The controller provides instructions to the data plane based on centrally configured policies. Functions include network discovery, resource abstraction pooling, and policy-based configuration.
So SDC, SDS, SDN, all about abstracting, pooling, and automating through software control.
That's the essence of software-defined infrastructure.
Now, putting this all together, how do organizations actually acquire and deploy this modern infrastructure? There are different infrastructure deployment options.
Yes, this is a major strategic decision. How do you get this capability? The traditional way was best of breed.
Meaning pick and choose.
Exactly. Organizations integrate hardware and software components purchased from many different vendors, trying to select the best product for each specific need. Best server from vendor A, best storage from vendor B, best network from vendor C.
What are the pros of that?
Maximum flexibility. You get the choice of what you perceive as the highest quality products from leading vendors for each component, and maybe less concerned about being locked into a single vendor for everything.
Sounds good, but what are the cons?
Significant cost and time. Evaluating, purchasing, testing, deploying, configuring, and crucially, integrating all these disparate pieces takes a huge amount of effort and expertise.
Which delays getting value.
Can severely delay time to market. Plus, you often end up with multiple different management tools, leading to siloed management, complexity, and potentially higher power and space requirements.
So, to combat that complexity, the industry came up with converged infrastructure, CI.
Right. CI takes a different approach. It integrates high-quality, pre-architected, pre-configured, and pre-tested hardware and software components into a single packaged solution.
All in one box, basically.
One rack, yeah. Network, storage, compute, virtualization software, management software, all bundled together and validated by the vendor. Examples given include VCE, vBlock systems.
What are the pros of CI?
It dramatically reduces the time and risk involved in deployment, improves time to market significantly. Because it's pre-integrated and optimized, it often leads to higher utilization rates, and it simplifies management, usually offering a single management interface for the whole stack. Frees up IT staff.
Any cons?
Flexibility of choice is obviously limited. You're buying the vendor's chosen components. And there's potentially more vendor lock-in for that integrated stack.
Okay. And taking CI even further, we have the really hot trend now, hyper-converged infrastructure, HCI.
HCI builds on the CI concept but takes integration even tighter. It typically pre-configures and manufactures compute, storage, and virtualization as a single appliance or node.
So compute and storage are in the same box?
Often, yes. HCI usually uses software-defined storage running on industry-standard servers with internal or directly attached drives, eliminating the need for a separate SAN. It delivers a validated solution with even greater performance potential, simplicity, and scalability.
How is it different from CI architecturally?
While CI is primarily about integrating existing hardware components, HCI relies heavily on a software-defined infrastructure layer running on top of commodity hardware, providing tighter integration and often more software-driven features. Dell EMC VX Rail and XE series appliances are given as examples.
What are the advantages of HCI?
Centralized management for consolidated workloads is a big one. It allows organizations to start small, maybe just a few nodes, and easily scale capacity and performance non-disruptively just by adding more appliances to the cluster. It's often optimized for specific workloads like virtual desktops, VDI, or business-critical applications with native automation tools.
And IDC research supports this.
Yes, the source mentions IDC highlighting simplified management, rapid scalability, and workload optimization as key drivers for HCI adoption.
Was there a real-world HCI example?
Yes, that rental service company with thousands of locations. They faced IT staff bogged down in administration and hitting infrastructure limits.
What happened when they deployed HCI? Dell EMC VxRail.
They dramatically simplified their IT operations, lowered costs, achieved rapid deployment, and gained simplified manageability and high performance. Critically, it freed their IT staff to focus on user-facing engineering efforts, adding more business value.
A powerful case study. So this all leads to a fundamental choice. Build your own, BYO, versus buy.
Exactly. When you're transforming your IT, you face this critical decision. Do you try to build your own custom IT solutions, using best-of-breed components, maybe even developing custom software? Or do you buy pre-engineered solutions like CI or HCI?
What are the arguments for BYO?
Full control, complete customization to your exact, perhaps unique business requirements. Software specifically designed for your analyzed needs.
And the downsides?
Consumes significant time, resources, and cost. Requires deep in-house understanding of requirements, technology integration, and the skills to build and maintain it. There's also a real risk of falling behind rapidly changing technology trends while you're busy building.
And the advantages of buying pre-engineered solutions.
Saves time, resources, and often cost, as the solutions are readily available and engineered by experts. Much faster installation and deployment. And you get access to vendor support and ongoing development.
So how do you decide?
You need to carefully consider your specific business requirements. Choose the right underlying technology approach. Analyze existing solutions in the market. Critically assess your required time to market. And be honest about the availability of the necessary skills within your organization. This decision has a massive impact on your agility and ability to innovate. V. The pillars of operation. Business continuity, security, and service management.
Okay, we've designed and deployed our modern infrastructure. Now we need to keep it running smoothly, reliably, and securely. This brings us to the pillars of operation. First up, business continuity, ensuring uninterrupted operations.
Absolutely vital. You can have the best infrastructure, but if it's not available, it's useless.
Let's start with cloud service availability. How is that defined and measured?
Availability simply refers to a service's ability to perform its agreed function during its specified operational time. It's often measured in nines.
Like 5 nines.
Right, 5 nines means 99.999% availability. That translates to only about 5.26 minutes of potential downtime per year. Extremely high availability.
What causes services to become unavailable?
Many things. Component failures are common. Compute hardware, storage drives, network links. Poor application design can cause crashes. Human error during configuration changes is a big one. Even routine IT activities like software upgrades or planned maintenance can cause temporary unavailability if not managed well.
So how do you ensure high availability? What are the solutions?
It requires a proactive approach. Redundancy is key, having backup components or entire systems ready to take over. This applies at the component level, like dual power supplies, and at the site level, multiple data centers. Robust data protection backup and replication is crucial. Automatic failover mechanisms are needed to switch to redundant systems quickly, and architecting resilient cloud applications that can handle failures gracefully is also important.
You mentioned redundancy. A core concept here is fault tolerance.
Yes, fault tolerance is the ability of a system to continue functioning correctly even when one or more of its components fail.
Protecting against different kinds of failures.
Right. It helps protect against transient failures, short one-time glitches, intermittent failures, problems that recur sporadically, and permanent failures, like a dead component.
And how is it achieved?
The core principle is redundancy, duplicating critical components or data pathways so that if one fails, another can take over the workload, ideally seamlessly.
Can you give examples at the infrastructure level? Let's start with compute.
At the compute level, compute clustering is common. You have at least 2 compute systems or hypervisors working together, appearing as a single system.
Different types of clusters.
Yes. In active-active clustering, all systems in the cluster are actively running the service and balancing requests. If one fails, the others just absorb its load. This enhances both performance and availability. In active-passive clustering, one system or more is idle, waiting to take over only if the active one fails.
Any specific technologies?
VMware vSphere HA, high availability, is an example. It automatically restarts VMs on other hosts if their original host fails. VMware FT fault tolerance goes even further, creating a live shadow instance of a VM that takes over instantly with zero downtime if the primary fails.
Okay. What about network-based fault tolerance?
Several techniques here. Link aggregation combines multiple physical network links between 2 points, like a server and a switch, into a single logical link. This increases bandwidth and provides failover. If one physical link breaks, traffic continues over the others.
Similar idea for server NICs.
NIC teaming groups multiple physical NICs in a server to appear as a single logical NIC to the operating system. This provides failover if a NIC or its cable fails, and can sometimes aggregate bandwidth too.
And connecting to storage.
Multipathing software allows a compute system to use multiple physical paths to connect to a storage system, often through different HBAs or network ports. If one path fails, I/O automatically continues over the remaining paths. It also enables load balancing across paths.
Okay, compute network. What about storage-based fault tolerance, protecting the data itself?
Critical. This protects against drive failures, controller failures, or even entire storage system failures. RAID, redundant array of independent disks, is a very common technique using multiple disk drives to provide protection against individual drive failures, depending on the RAID level.
Anything beyond RAID?
Erasure coding is becoming increasingly popular, especially in large-scale object storage. It breaks data into fragments, encodes them with redundant information, and spreads them across different drives or even different locations. It can often tolerate more simultaneous failures than traditional RAID, while being more space efficient.
What about protecting against whole system failure?
Storage resiliency using virtualization is key. Techniques like mirroring LUNs, volumes, across 2 different storage systems, ensure that if one entire system fails, the surviving mirror leg on the other system can continue processing I/O requests.
So fault tolerance at the component level is crucial. What about bigger disasters, site-level fault tolerance?
This is about surviving major outages, like a fire, flood, or power failure, affecting an entire data center. The solution is to deploy multiple service availability zones.
What are those?
It's essentially multiple geographically dispersed data centers that are independent but connected. By deploying your service across multiple zones, you ensure it can survive even if one entire zone goes offline. Seamless, often automated, failover between zones is critical here.
And finally, the applications themselves need to be resilient. Application resiliency.
Absolutely. You can have resilient infrastructure, but if the application isn't designed to handle issues, it will still fail.
How do you build resilient apps?
One concept is graceful degradation. The application maintains limited functionality, even if some components or dependent services are unavailable. Remember that e-commerce example? Maybe the product recommendations fail, but you can still browse and buy.
Better than a total crash.
Much better. Another is implementing fault detect and retry logic in the code. If an operation fails due to a temporary glitch, like a network blip, the code automatically retries it a few times before giving up.
What about application state?
Designing applications using a persistent state model, often meaning making them stateless, is important. If an application instance fails, a new one can start up without losing user session information, making scaling and recovery easier. Checkpointing, periodically saving the application state, can also help recover from the last known good point.
Okay, keeping things running is vital, but protecting the actual data is just as important, right? Data protection, securing your most valuable asset.
Absolutely critical. Protecting data is paramount. Organizations often use a tiered approach here.
Tiered approach.
Based on the importance of the data. Mission-critical data, Tier 1, gets the highest level of protection, while less critical data, Tier 3 maybe, gets a less rigorous, perhaps less expensive protection strategy.
What are the main data protection methods? Backup seems fundamental.
Backup is the process of creating copies of data that can be used for recovery if the original data is lost or corrupted.
How has backup evolved in virtual environments?
It's moved from agent-based backup inside each server to more efficient image-level backup. This copies the entire VM, often via a proxy server, without needing agents inside the guest OS. It still usually supports granular file-level recovery from that image.
And a major innovation backup is deduplication.
Deduplication has been a game changer. It intelligently detects and eliminates redundant data segments before or during the backup process.
So you don't back up the same block of data multiple times.
Exactly. If the same file or even parts of files exist across many servers, deduplication stores it only once and uses pointers for the duplicates.
Where does deduplication happen?
It could be source-based, happening at the backup client before data is sent over the network. This saves bandwidth. Or it can be target-based, happening at the backup storage device itself, either inline as data arrives or post-process after it's initially stored.
What are the benefits of deduplication?
Huge benefits. Reduces backup storage capacity needed, sometimes dramatically. This lowers infrastructure costs, storage hardware, power, cooling, enables longer retention periods for backups, reduces backup windows, and minimizes network bandwidth consumption, especially with source-based dedupe.
Where can backups be stored in a cloud context?
Several options. Local backup, managed by the cloud service provider for data hosted in their cloud. Remote backup, where a consumer backs up their on-premise data to the CSP's cloud. Or even replicated backup, cloud-to-cloud backup for extra protection.
Okay, backup is for recovery from loss. What about archiving?
Archiving is different. It's about moving data that is no longer actively used but needs to be kept, often for compliance or legal reasons, to lower-cost storage tiers for long-term retention.
So it frees up expensive primary storage.
Exactly. Data is moved, not just copied. Archives can be stored on-premise or, increasingly, in cheaper cloud archive storage tiers.
And the third key method is replication. How does this differ from backup?
Replication is about creating exact copies, replicas, of data, often in near real time, at a secondary location. The primary goal is typically much faster recovery and restarting operations compared to restoring from backup. It's more about business continuity than just data recovery.
What are some replication techniques? Snapshots.
Snapshots are point-in-time copies, often of a file system or volume. They're frequently pointer-based, using techniques like copy on write or cut of view, and very fast to create, providing quick recovery points. However, they usually rely on the original data still being intact.
What about replicating to another site? Remote replication.
Yes. This copies data to a secondary site. It can be synchronous, where writes aren't acknowledged back to the application until they are committed at both the source and the target site. This guarantees zero data loss, near zero RPO recovery point objective, but adds latency, especially over long distances.
Or it can be
Asynchronous. Here, writes are acknowledged immediately at the source, and the changes, delta sets, are transferred periodically to the target. This minimizes the impact on application response time, but means there might be a small amount of data loss, a higher RPO, if a disaster hits between transfers. Continuous data protection, CDP, is an advanced form that replicates continuously, allowing recovery to virtually any point in time.
And cloud plays a role here too. Cloud-based replication.
DR. Yes, disaster recovery as a service, DRs, has become a very viable option. The cloud provider essentially provides the secondary site and resources needed to continue IT services in case of a disaster at the primary site.
Right.
This can be much more cost-effective for the consumer than building and maintaining their own secondary DR site.
The source mentions several Dell EMC and VMware tools for data protection.
Yes, it listed tools like Avamar, source-based dedupe, Data Domain, target-based inline dedupe with data integrity checks, Networker, centralized backup management, Mosey, cloud backup SaaS, Cloud Boost, enabling backup to cloud, Apache, backup replication focused on low RTOs, and RecoverPoint, CDP, and also VMware vSphere Replication and Site Recovery Manager for VM replication and DR orchestration. Shows the breadth of solutions available.
All right, continuity and data protection covered. Now, the big one, security. The imperative for trust in the cloud. This feels more critical than ever.
It's absolutely paramount. Information security is non-negotiable in today's digital world. Data breaches are incredibly costly.
That's cited a Ponemon Institute study.
Yes, $3.62 million average cost per breach back in 2017, and that's just the direct cost. Breaches can lead to stolen IP, massive financial losses, regulatory fines, and devastating reputational damage. Think about the impact of attacks like WannaCry.
So security can't be an afterthought.
Never. It has to be built in from the start, considered during architecture and design, with sufficient budget and time allocated.
How does cloud computing change the security game?
Cloud's unique features that shared resource pooling, the rapid elasticity, the broad network access, they introduce new security challenges and attack surfaces. Trust becomes absolutely critical, and that trust depends heavily on having appropriate control and visibility.
This is where governance, risk, and compliance, GRC, comes into play for cloud providers.
GRC provides the essential framework for providers to operate ethically, manage risks effectively, and adhere to all the necessary regulations.
Breaking down GRC, governance.
Governance is about defining the policies, principles, and procedures that guide security operations.
Yeah.
It establishes clear contracts and responsibilities between providers, consumers, and even third-party vendors, especially where outsourcing might reduce direct control. Risk is the effect of uncertainty on business objectives. Risk management in the cloud involves identifying potential threats and vulnerabilities, assessing their likelihood and impact, implementing mitigation strategies, controls, and continuously monitoring the situation. Cloud insurance is even emerging as a risk management approach.
And compliance.
Compliance means adhering to external laws, regulations like GDPR, industry standards like TIPO for healthcare, PCI DSS for payment cards, and internal corporate policies. There are also cloud-specific frameworks like the Cloud Security Alliance's CSA, Cloud Control Matrix, CCM, that help organizations assess provider compliance.
Okay, GRC sets the rules. What are the fundamental key information security concepts everyone needs to understand?
The absolute core is the CIA triad: confidentiality, integrity, and availability.
Confidentiality.
Ensuring data is accessed only by authorized users and processes. Keeping secrets secret.
Integrity.
Ensuring data is accurate, complete, and trustworthy. Preventing unauthorized modification.
And availability.
Ensuring data and resources are accessible and usable when needed by authorized users. The system is up and running.
Beyond CIA.
Accountability is crucial. Actions need to be traceable back to specific individuals. Authentication verifies a user's identity. Who are you? This can be single-factor, like just a password, or, much better, multi-factor, like a password plus a code from your phone. Authorization determines what an authenticated user is allowed to do. What privileges do you have?
And data ownership.
A critical point: data ownership and localization. The consumer always owns their data, regardless of where it's physically stored in the cloud. Contracts should specify data location and jurisdiction requirements.
How do you structure security effectively? The source mentions defense in depth.
Defense in depth is a fundamental security strategy. It involves implementing multiple layers of security controls: physical, network, compute, application, data. The idea is that if one layer is breached, other layers are still in place to provide protection. No single control is relied upon entirely.
And the trusted computing base, TCB.
The TCB refers to the set of all hardware, firmware, and software components within a system that are critical to its security. If any part of the TCB is compromised, the security of the entire system could be jeopardized. That's why minimizing the TCB, like using a bare metal hypervisor instead of a hosted one, can potentially improve security by reducing the attack surface.
Okay, let's talk threats. What are the common security threats in the cloud environment?
It's a challenging landscape.
Yeah.
Data breach, unauthorized access to sensitive data is a major one, often caused by compromised credentials, application flaws, or malicious insiders.
What else?
Identity, credential, and access management issues, things like weak passwords, lack of multi-factor authentication, poorly managed identities that don't scale or rotate keys properly. Insecure application programming interfaces, APIs, are a huge risk, as APIs are the connective tissue of the cloud. Vulnerabilities here can open doors to the entire infrastructure.
System vulnerabilities.
System and application vulnerabilities, yes. Exploitable bugs, including zero-day vulnerabilities, flaws unknown to the vendor that hackers use to gain access, account hijacking through phishing or malware.
What about threats from inside?
Malicious insiders, current or former employees, contractors, partners, misusing their legitimate access. IBM reported back in 2015 that insiders cause 60% of attacks. Significant threat.
Or sophisticated attacks.
Advanced Persistent Threats, APTs. These are long-term, stealthy attacks, often state-sponsored or highly organized crime. They gain initial access, maybe via spear phishing, then move laterally within the network, quietly harvesting information over extended periods, adapting to security measures. Very hard to detect.
Other threats.
Simple data loss, not necessarily malicious, could be accidental deletion or a natural disaster. Providers need clear protection mechanisms. Abuse and nefarious use of cloud services, criminals using cloud resources, often free trials, for things like DDoS attacks, hosting malware, or running phishing campaigns. Denial of service, DOS, or distributed DOS attacks aimed at overwhelming resources to make services unavailable to legitimate users. And finally, shared technology issues, potential failures in multi-tenancy mechanisms, like a hypervisor vulnerability that could expose one consumer's data or processes to another.
That's a daunting list. So how do you fight back? What are the security controls and mechanisms?
You need a proactive approach, investing in the right policies, processes, and technology controls. Controls can be categorized by their function. Preventive controls aim to stop attacks from happening in the first place, e.g., strong authentication, firewalls, physical security. Detective controls identify attacks that are happening or have already happened, for example, intrusion detection systems, security logs, audits. Corrective controls help reduce the impact of an attack and restore the system, e.g. restoring data from backup, patching vulnerabilities.
And these controls involve?
People, process, and technology. Administrative security includes security policies, standard operating procedures, personnel security like background checks, and security awareness training. Physical security is about securing the actual data center facility, access control, guards, surveillance, redundant power cooling, environmental sensors, restricting visitor devices.
And the technology part, technical security.
This is where the tools come in. Critical areas include identity and access management, IAM, using things like multi-factor authentication, MFA, digital signatures for verifying identity, single sign-on, SSO, for convenience and better control, and role-based access control, RBAC, to enforce least privilege.
Securing the apps themselves.
Application security, using secure coding practices, doing threat modeling during design, maybe using sandboxing to isolate untrusted code. Operating system, OS, hardening, removing unnecessary software, applying security patches promptly, configuring systems according to security benchmarks like CIS or DISA, running vulnerability scans, and performing penetration testing.
What about the virtualization layer?
Hypervisor hardening is crucial. Things like separating management networks from VM networks, installing security updates, restricting access, disabling unused services, and similarly, virtual machine, VM, hardening, changing defaults, disabling unused virtual hardware, ensuring guest OS security tools are active, using VLANs to isolate VM networks.
Network security controls.
Firewalls are fundamental, monitoring and filtering traffic between networks. Cloud environments use network-level firewalls or firewall as a service, FYSS. Demilitarized zones, DMZs, are often used to segregate internet-facing systems. Intrusion detection and prevention systems, IDPS, look for malicious activity, either signature-based, known attack patterns, or anomaly-based, deviations from normal behavior. Network segmentation using VPNs, VLANs, or vSANs helps contain threats.
What about mobile devices?
Mobile device management, MDM solutions like VMware AirWatch mentioned in the source are needed to monitor, manage, and secure employee mobile devices accessing corporate resources.
Can you get security from the cloud?
Yes, security as a service, SecAS, is where cloud providers offer security functions like IAM, IDPS, encryption, antivirus, as a subscription service. This can reduce the burden on the customer and leverage the provider's expertise.
The source mentioned tools like RSA Data Protection Manager and Dell EMC Cloud Link.
All right, examples of tools for encryption key management and data at rest encryption, reinforcing that defense-in-depth approach. Tools like RSA Net Witness Suite for incident detection investigation and Dell Change Auditor for tracking user activity are also part of this technical security landscape.
Okay, continuity and security are vital. The final pillar is service management, governing and operating cloud services. What does this cover?
Cloud service management encompasses all the processes and functions needed to actually provision, manage, and govern cloud services effectively throughout their lifecycle.
How does it differ from traditional IT service management, like ITL?
It adapts those traditional processes for the cloud context. It has to handle increased flexibility, complexity, multi-vendor, multi-data center environments, and potentially higher risk exposure. It relies heavily on automation and workflow orchestration to achieve the speed and elasticity required by cloud.
What are the key functions within service management?
Broadly, two main areas: service portfolio management and service operation management.
Let's start with service portfolio management. What's its goal?
This is about defining the overall suite of service offerings. It involves aligning services with strategic business goals, deciding where to invest, ensuring services are delivered cost-effectively, and managing the overall portfolio like a business.
What functions fall under this? Service catalog management.
Yes. This function is responsible for designing, implementing, maintaining, and updating the service catalog, that menu of services we discussed. It provides different views: a detailed one for administrators, and a consumer-facing view showing service descriptions, value, policies, costs, etc.
What about the money side, financial management?
Crucial. This manages budgeting, accounting, and billing for cloud services. It involves financial planning, service valuation, determining the price to recover costs and ensure profitability or ROI, and cost modeling. This is where concepts like chargeback, actually charging business units for consumption, and showback, just reporting the costs, are implemented. Different chargeback models exist: pay-as-you-go, subscription, fixed cost, etc.
And managing external providers, supplier management.
Yes, managing relationships with external suppliers, like public cloud providers or software vendors. This involves negotiating contracts, periodically evaluating supplier performance against SLAs, managing the relationship to ensure alignment with business strategy, and mitigating risks like vendor lock-in. The source mentions using supplier performance reports to decide on contract renewals.
Okay, that's defining the services. Now the day-to-day running, service operation management.
This focuses on maintaining the cloud infrastructure and all the deployed services to ensure the committed service levels, SLAs, are consistently met. This area is heavily automated through cloud service management tools.
What's the foundation here? Monitoring, alerting, and reporting.
Absolutely the foundation. You can't manage what you can't measure. Monitoring is the continuous tracking of cloud infrastructure and services, checking configuration, availability, capacity usage, performance metrics, security events. It provides end-to-end visibility and collects historical data for trending. Tools like Amazon CloudWatch or VMware vRealize Operations are examples. The source gave examples like monitoring OS versions for compliance or tracking server memory usage to prevent outages.
Alerting.
Alerting provides timely notifications when monitoring detects critical events, performance degradation, a service going down, a security policy violation. Critical alerts get prioritized, and often automated recovery actions can be triggered directly from an alert.
And reporting.
Reporting takes the raw monitoring data and formulates it into meaningful reports for analysis, tracking trends, capacity planning, identifying areas for improvement. These can be dashboards for IT staff or usage and billing reports for consumers.
Keeping track of all the components and their relationships sounds complex. That's Service Asset and Configuration Management, SACM.
Yes. SACM maintains detailed information about all the configuration items, CIs, which could be services, hardware, software, documentation, even people, or SLAs, and crucially, the relationships between them. This information is stored in a configuration management system, CMS, often a federated database. Discovery tools often automate the process of finding CIs and updating the CMS.
What about managing changes, change management?
Given the dynamic nature of cloud, change management is vital. It oversees all changes to CIs in a controlled way to minimize any adverse impact on business operations. Low-risk, standard changes might have automated approval workflows, while more significant changes are reviewed by a Change Advisory Board, CAB, to assess risk, impact, and priority.
Ensuring you have enough resources. Capacity management.
Capacity management ensures the cloud infrastructure has sufficient capacity to meet current and future demands cost-effectively and in a timely manner. It prevents service unavailability due to resource exhaustion, like running out of CPU or storage. It involves monitoring usage trends, forecasting future needs, and planning upgrades or resource allocation changes. The source showed an example of expanding a storage pool via an orchestrated workflow triggered by capacity monitoring.
How well are things running? Performance management.
Performance management focuses on evaluating how efficiently services and infrastructure components are performing. It examines metrics like response time, throughput, utilization rates to identify bottlenecks and areas for tuning. Administrators might allocate more memory to poorly performing VMs or migrate services based on performance data.
What happens when things break? Incident management.
Incident management's primary goal is to restore normal service operation as quickly as possible after an unplanned interruption occurs. It involves logging incidents, diagnosing them, potentially escalating to technical experts, implementing workarounds or temporary solutions, and tracking the resolution time against SLAs.
And preventing recurrence. Problem management.
Problem management aims to prevent incidents with common symptoms or underlying root causes from happening again. It involves deeper investigation, often correlating multiple related incidents, identifying the root cause, and implementing permanent solutions or changes to prevent recurrence.
Availability management and information security management are also part of operations.
Yes, availability management focuses proactively and reactively on ensuring services meet their availability targets throughout their lifecycle. Information security management ensures security policies are enforced, risks are continually assessed, and security controls are deployed and managed effectively within the operational environment. The source showed a security architecture example with virtual firewalls enforcing traffic flow between service tiers.
The source listed several management tools here too.
Yes, Dell EMC Open Manage for systems management, Dell Boomi for integration, VIPR SRM for storage reporting, CISv3 for customer service dashboards, Data Protection Advisor for backup monitoring, and the VMware vRealize suite, including operations, for automating performance, capacity, and configuration management. A Columbia Sportswear case study highlighted using vRealize for faster hybrid cloud service delivery. 6. The human and process side of transformation.
We've covered a massive amount of technology, architecture, and operational processes, but digital transformation isn't just about the tech, is it? It's also fundamentally about people and processes.
You're absolutely right. That's often the hardest part. IT transformation requires transforming IT operations, and at its heart, that means transforming the people who do the work and the processes they follow.
So let's talk about people transformation, the cultural shift.
This is huge. A key success factor for any digital transformation is cultural change, shifting the mindset and operating style of the organization, especially within IT. Leaders need to understand this and actively guide the cultural shift.
What does that mean for the workforce? Upskilling.
Definitely. Existing IT staff often have deep skills in traditional infrastructure managing specific servers or storage arrays. They need to be upskilled for this new world of cloud services, automation, and software-defined everything. Training programs are essential to help them understand business priorities, customer needs, and the new technologies.
Does it create new roles?
It does. Cloud adoption introduces roles that didn't exist before or become much more prominent. Service manager, cloud architect, cloud engineer, DevOps engineer, cloud administrator. The focus shifts.
And how teams are structured. The source mentions cross-functional teams.
Yes. Breaking down those old IT silos is critical.
Yeah.
Creating teams with people from diverse backgrounds, operations, development, security, maybe even finance or business units working together towards common goals, fosters creativity, improves communication, and leads to better, faster solutions.
So collaboration and communication become even more vital.
Essential for continuous innovation. Teams need the culture and the tools for real-time chat, shared documentation, and collaboration. DevOps tools often integrate automated communications and notifications as part of the workflow.
Okay, people are key. What about the processes they use? Process transformation, agility, and automation.
Traditional IT processes, often slow, manual, ticket-based with lots of handoffs, are frequently unsuitable for the speed and dynamism required by cloud services. Process transformation, really rethinking and streamlining how work gets done, is critical.
And the key enabler here is automation.
Automation is absolutely key. Automating end-to-end IT processes, everything from provisioning a new server or service to patching systems to resolving common IT tickets, has massive benefits. Reduces service provision time dramatically. Improves developer productivity, they get resources faster. Reduces the complexity and cost of infrastructure management, and crucially, minimizes human errors, leading to more reliable services.
How do organizations approach improving processes?
They need to adopt continuous process improvement, always looking for ways to streamline, automate, and eliminate waste. Standard frameworks like ITIL, Information Technology Infrastructure Library, TOGIF, the Open Group Architecture Framework, and COBIT, Control Objectives for Information and Related Technologies, can provide guidance here, adapted for the cloud context.
And a major methodology that brings people and process transformation together is DevOps.
DevOps has been revolutionary. It's a methodology, a culture, and a set of practices where software developers, dev, and IT operations staff, ops, collaborate closely throughout the entire service lifecycle, from design through development and testing to production support.
Breaking down the wall between dev and ops.
Exactly. What are the benefits?
The source highlighted some impressive stats: faster application development and delivery, quicker incorporation of user feedback and changing demands, reduced costs, and significantly faster recovery from failures.
Yeah, that Puppet survey finding was striking. High-performing DevOps organizations recovered from failures 24 times faster, and they deployed code 200 times more frequently than lower-performing peers. That's a staggering difference in agility.
How do they achieve that? What are the core practices?
DevOps relies heavily on building an integrated, automated tool chain that covers the entire software delivery pipeline. This minimizes manual steps, reduces errors, and provides rapid feedback.
Including continuous integration, CI.
CI is fundamental. Developers frequently merge their code changes into a central repository, like Git, multiple times a day. Each merge automatically triggers build and integration tests.
What's the point of doing it so often?
It provides very early feedback. If an integration fails, you know immediately and can fix it quickly when the change is small. It prevents the nightmare of integration hell where multiple large changes conflict later on.
And continuous delivery, CD.
CD extends CI. After the CI build and basic test pass, CD adds a further suite of automated tests, acceptance tests, performance tests, security scans, and an automated deployment pipeline.
So deployment is automated too.
The goal of CD is to ensure that the software can be reliably released to production at any time, often with the push of a button. It might still involve a manual approval for the final deployment, but the process is fully automated and tested up to that point. Some organizations go further to continuous deployment, where every successful build is automatically deployed to production, enabling extremely rapid iteration. The key is low risk and high reliability through automation.
And managing the infrastructure itself in this automated way leads to infrastructure as code.
IAC. IAC is a critical DevOps practice. It means managing and provisioning your infrastructure, servers, databases, networks, load balancers, firewalls using definition files, using code, essentially, just like application source code.
So you write code to define your infrastructure.
Exactly. These definition files are stored in version control, like Git, reviewed, tested, and applied automatically.
What are the benefits?
It allows for versioning of your infrastructure. You can track changes, revert if needed. It enables full automation of infrastructure deployment, making it fast, repeatable, and consistent across different environments. Dev, test, prod. Tools like Chef, Puppet, Ansible, and Terraform are commonly used for IAC. It treats infrastructure as just another programmable, versionable component of your system. Outro.
And with that, wow, we have covered a lot of ground. A truly deep dive into the foundational components of modern IT infrastructure.
We really went from the fundamentals up through the layers.
From the NIST definition and characteristics of cloud through IASP and AS, saw the different deployment models.
To how modern applications are built with microservices and containers.
The physical, virtual, and software-defined infrastructure layers.
And crucially, those pillars of operation. Business continuity, security, and service management, plus the people and process side.
You should now have a really comprehensive, clear, structured understanding of what makes modern IT tick.
And why these elements are absolutely essential for any digital business today.
Yeah, this isn't just abstract theory anymore, is it?
Not at all. These are the practical realities, the strategic choices that businesses are making right now, every single day, to stay competitive, to innovate, to survive.
The shift is profound. From monolithic apps to microservices, from buying hardware to consuming services, from manual processes to automation.
It really is a different world.
So, to leave you with something to think about, as IT keeps evolving at this ever-accelerating pace, what aspect of this modern infrastructure we've discussed today do you think will undergo the most radical transformation in, say, the next 5 years?
Good question. And how might that completely reshape how we think about IT all over again?
Something to ponder. We'll leave you with that thought.
Until next time on The Deep Dive, keep digging for knowledge.